Hello, in this video we're going to do the second ANOVA example, and I just realized I didn't have that on here, so ANOVA example 2 is now saved on. So it's the same similar scenario about the 40-point exam and that you've got the classical nature and nothing sounds. We are doing an ANOVA with this data similar to why we did the first time, and that's because we have one categorical variable. So one categorical variable, but that one categorical variable has 3 or more groups. If it was like this, but it only had 2 groups, it would be an independent samples t-test. But because we've got 3 or more groups, and then we have one numeric variable, and the numeric variable is test scores, that is why it's an ANOVA. So ANOVA is very similar to the independent samples t-test. The only difference is you're just adding an extra independent group. So for example, if we just had these 2, this would be an independent samples t-test. By adding this third one in, that's what makes it an ANOVA. So for the hypothesis, there is no significant difference. That's the null. So once again, null, there is no significant difference. Alternative is that there is a significant difference. We're going to go ahead and run the statistical test in JASP. The first step is creating that data in JASP. And I went ahead and I already have it created. So sorry, I didn't mean to cheat. If you need help seeing how to create this in JASP, make sure to check out that first example. The big thing is just, going ahead, creating the data set, using the room to make sure that you've got your room set up correctly, and then entering in also those test scores, and then double checking that you have all your data. So we have all the data, we've got it in. Once again, if you need help figuring out how to get the data into JASP, make sure and watch the first ANOVA example. So in the first ANOVA example, I show exactly how to do this. So even though this is new data, I just wanted to try to speed things along. So we've got the data in. We're then going to go up to ANOVA and classical. And this is really important. It does need to be classical ANOVA. Then remember that dependent variable, that's the thing we're measuring, is the test scores. And then our fixed factor is the room. That's that fixed factor. So we do have our initial ANOVA results, which is great, but we need more stuff. So we're going to add our descriptive statistics. Under the assumption checks, we're going to add our homogeneity tests. Under post hoc test, we're going to go ahead and add the room and add the effect size. And we're going to flag significant comparisons. So those are all of the different things that you need to check off the box, or check off, the different boxes and things to do. So these are the results. You would want to go ahead and copy these results and paste them in. So go ahead, copy, get your snipping tool or whatever it is you use. Make sure to copy these, paste those into a Word document, and let's go ahead and take a look at the results. So first step is how to interpret that Levene's p-value. And so Levene once again checks whether the variance of the 2 groups are approximately equal and is used to test the statistical assumption of homogeneity of variance. Unlike the interpretation of a normal p-value, for Levene you want a high p-value. Unfortunately, if we look at this Levene p-value, we can see that it's 0.014. That means that it's less than or equal to 0.05, which means variances are significantly different. We do not want variances to be significantly different. So in this case, because they are, it means that this data is not suited for a regular ANOVA. So because our variances are not significantly different, this data is not appropriate for an ANOVA. Instead, what we need to do is make the switch to a non-parametric Kruskal-Wallis test. So since we can't do the ANOVA thanks to this Levene score, and that's because this Levene p-value is so small, we're going to go ahead and switch to the non-parametric Kruskal-Wallis test. So for this test, what we're going to do is come over here, and if you scroll all the way down, we have this non-parametric option. So we're going to go ahead and select it, and then add the done post hoc test results. So that's all you have to do to add those extra test results. And remember, the only reason we're doing this is because of this Levene p-value. So because this Levene p-value is small, it means the variances are not different, and it means we can't use this data for ANOVA. Instead, we need to switch to the Kruskal-Wallis. So basically what that means is we're crossing out all of this information because we're not using any of that information. Instead, we're going to use the Kruskal-Wallis test, but we also, similar to that independent samples t-test, we're now using the median value for each group instead of the mean value. So to do that median value, we're going to go up to descriptives, descriptive statistics. Our variable is test scores, and the split is the room. Then underneath statistics, we can uncheck all of this stuff. And we do want median, we don't want any of that. And there we go. And so then you would just want to go ahead, use that snipping tool to snip that information, and you are good to go. We now have everything we need. So we've got the Kruskal-Wallis test information and the descriptive statistics information with the median. Because remember, once we switch to the Kruskal-Wallis, that non-parametric test, we are no longer using the mean for comparison, we're using the median. So how do we interpret that Kruskal-Wallis? Oh, and also, I didn't include it up there, but I included below. We do need the done post hoc results. So back up here, make sure you get these done post hoc results because those are really important results. So make sure you get these done post hoc results. So make sure you copy that over. Okay, so how to interpret the Kruskal-Wallis p-value? Just the same way that you would the ANOVA p-value. If p is less than or equal to 0.05, that means that we do have significant results and we are rejecting the null. So in this case, that p is 0.001, which is much smaller than 0.05. So it means we reject the null and we do have significant results. In terms of interpreting the post hoc comparisons, when Kruskal-Wallis results are significant, and these were significant because we rejected the null, it indicates that at least two of the groups are different from each other. So this is very similar to what we did with the Tukey. So the whole idea of these post hoc results, exact same as what we did for the regular ANOVA. The only difference is that we're using done post hoc instead of Tukey post hoc. So basically the post hoc just lets you know which groups are significantly different, and you can tell by looking at the p-value for the Dunn's post hoc comparison. And so for this one, it is specifically the p Bonferroni, and it's BONF, but it means p Bonferroni. And that's kind of a fun word, isn't it? Bonferroni. But on this table, what you're looking at is the p BONF, standing for the p Bonferroni, and you're looking for whether or not the groups are different, which means the p is going to be less than or equal to 0.05. So in this case, when you look at these p Bonferroni results, you can see that the classical versus nothing and the nature versus nothing groups are significantly different. There is no significant difference between classical and nature. So down here in our written results, ANOVA was done to determine if there was a significant difference in test scores for students in the different rooms. Our null was that there's no significant difference. Our alternative is that there is a significant difference. A Levene test found that the assumption of homogeneity of variance was not met. Make sure to provide that p-value. Italicize the p, no leading zeros. Due to variances being significantly different, the data was not appropriate for an ANOVA, so a Kruskal-Wallis non-parametric test was performed. It was determined that there is a significant difference between students who are in the classical room. Sorry, that sounded a little funny. The classical room. And then make sure it's that median now. So that median, make sure it's italicized. So we're in the classical room, nature room, and nothing. Then for your results, the results do look a little bit different. We've got H because it is an H test. It is a Kruskal-Wallis H test. And I don't think it shows anything. Yeah, it doesn't say that it's the H statistic, but it is an H statistic. So it is H. So it is italicize the H. The 2 for the degrees of freedom is already provided right there for that Kruskal-Wallis test. Then we've got the H value from the Kruskal-Wallis test, and then the P value from the Kruskal-Wallis test. The null hypothesis was rejected, and that's because these results were significant. So the null hypothesis was rejected, and post hoc testing was needed. Post hoc testing using Dunn's test with Bonferroni correction indicated that students who listened to classical compared to nothing, and that's that Bonferroni p-value right there, and nature compared to nothing, and then there's that Bonferroni p-value, scored higher. There was no difference between listening to classical music and nature. So this is how you would write up those results if you needed to switch and do the Kruskal-Wallis test. I hope this helps, and if you have any questions, let me know.